Rockpile Tutors with the first of a series of videos on probability and statistics. Part 1, we're going to do permutations and combinations. And as usual, I don't do this alone. Got my sidekick Gumbo. Say hey Gumbo, how you doing? Yeah, Gumbo's here. He corrects me when I make mistakes, and he has a lot to do. All right, let's get going. All right, the fundamental counting principle is what we're going to start with. And this is what we use to figure out how many different things can happen in a given scenario. So we're going to take an example of a restaurant. When you go, you have 5 different options for drinks. And then you have 6 meal choices, 6 main meal choices. And then there are 3 dessert choices. So how many different ways could you order a meal in this restaurant? And one of the best ways to visualize this is to use a tree. So let's just name our drinks A, B, C, D, and E. First thing you do when you come in, you sit down, you order a drink, right? In this case, let's say we chose drink B. Now you've got your drinks and you're going to place your order for the main course. Now here, we could have picked any drink, but since we chose B, then I'm going to have 6 different options of main courses. And the 5 is looking especially good tonight, so that's what we're going to be ordering. And now every other choice that you had for drink also would have had those 6 choices. So we're up at, a much larger number of possibilities now. And now your meal is done, and they come around and they ask if you'd like dessert, and of course the answer is yes. And so we have 3 different types of dessert, M, N, and P. And so if we started looking at all the different ways that we could order a meal, we chose B5N, right? Somebody else could have chosen E2P, right? And how do we figure out how many of those there are? There's obviously a whole lot of them. And so what we do is we multiply all the choices together. So any one of 5 could have been our first drink, and then each of those had 6 options for the main course, and then however we got there, we multiply by 3 for the desserts, and we end up with there are 90 different meals that could be ordered. And that is an example of the fundamental counting theory. We'll do a couple more examples. All right. First, what we're going to do is we're going to look at a license plate example. So on Rockpile Island, our license plates have 7 spaces. The first 3 are letters, and the last 4 are numbers. That's a 7. And so what we want to know is how many different license plates are there. So let's think about these 3. First, I've got every letter available, so my first, I'm going to have 26 options. Second one, because there's no problem with repeating decimal or repeating numbers, I've also got 26 options here, and the same as the third, which gives me 26 to the third options just for the letters. When I do the numbers, how many options do I have? I've got 10 different digits. So that's going to be 10 times 10 times 10 times 10, which is going to be 10 to the 4th. If I multiply those two together, you can see over here that I end up with 175,760,000 different license plates that have 3 letters and 4 numbers. All right, another example we can look at is a website password. Now everybody knows that they're increasing the number of places in a password they'd like you to have. And in our system, we've got a 10-digit passcode, 3, 4, 5, 6, 7, 8, 9, 10. And the other things we've got going is that we can have any letter, and capital letters are treated differently than lower letters. That goes all the way to Z, but my lowercase z's don't look that much different. And we can use 6 special characters. So we can also use the @ exclamation point, question mark, hashtag, and $. 1, 2, 3, 4. $, and what else can we do? Oh, the ampersand. I can never draw an ampersand. So those 6 characters, but not in the first or last spot. So let's count up our options. I said there are 6 of these. There are 26 different capital letters, and there are 26 small letters. So for all of them, I have 52 options, but for all but the first and last, I also have 6 more. So I'm going to have 58 here, and 52 here, a bunch of 58s, a bunch of 58s, and you can ignore this over here. I obviously wasn't thinking very clearly. 58, 58, 52, and if I add them, if I multiply them all together, I can do whatever order I want. So that's going to end up being 52 squared times 58 to the 8th, which is 2.61 times 10 to the 17th, which means 267 with 17 zeros after it. Whole lot of different combinations, very difficult to get through. Hopefully that makes sense, so that we generally multiply the different options that we get in order to find out how many different possibilities there are. And we're going to use that for the rest of probability and statistics. All right. So what are permutations and combinations? So permutations are the way you can group things when the order matters. So let's say that there are 10 students, right? And my job is to pick out the 4 favorites, right? So I like this student the best, this student the second best, third best, and fourth best. And so that order matters because it really is important to be number 1 versus number 2, number 3, or 4. So when order matters, we do permutations. Right? Other examples are when you have a race. Obviously, the Olympics gives out first, second, and third place. President, vice president, and secretary, instead of creating a committee, if you're voting for the president, the vice president, and the secretary, then which one is which does matter. And then license plates. You can't, ABC is different than CBA in a license plate, and so that's where order matters. A combination is when we're picking something like a committee, where I've got 10 people, and my committee is 4 people, right? So every year I have a different 4 people, but there's no order of them. They're just 4 out of the 10. So when order doesn't matter, similarly poker hands. So if you have ace 3, 6, ace 2, right? That is the same as ace 6, ace 2, 3. Right? The order of the cards doesn't matter. All that matters is the what the cards hold. And so that's where you use combinations. And they're going to be very similar formulas, but the difference is crucial, and understanding why you use the different permutations and combinations is important to understand what we do when we have combinations versus permutations. Okay, so let's look at ordering 4 objects. We have A, B, C, and D. Very creative. Okay. How many different ways can I organize these when order matters? So I can have A, B, C, D, A, B, D, C, right? It'd be a whole lot of them. And so essentially, because I have to use them all, I'm going to have 4 options for the first one, 3 options for the second one, 2 options for the third, and then when I choose that third, it forces me into that fourth. So I've got 24 different ways to organize A, B, C, and D. Now, if I were to look at combinations, there would only be one combination because they all include A, B, C, and D. Where the difference shows up is when you have less than all of them being taken care of. Because if you're choosing all of them, your combination is going to be the same no matter which order you pick them in. So let's look at an example where we will have a difference. So now I'm going to take those same 4 objects and I'm going to only pick 2 of them. Okay? So let's take a look, right? Let's make a tree. So for A, my choices are B, C, and D. For B, my choices are A, C, or D. C has A, B, and C, and D has A, B, and D, sorry, and D has A, B, and C. So if I list all of these out, I've got A, B, A, C, A, D, B, A, B, C, B, D, C, A, B, C, B, C, D, D, A, D, B, D, C. These permutations, if I count them up, are 4 choices for the first times 3 choices for the second, which gives me 12. So now how many combinations? So if you look at these 12 from a combination where order doesn't matter, AB is going to be the same as BA. And so each of my choices will have a flipped version. And so I'm going to divide by 2 to get the 6 pairs or the 6 combinations, and the order doesn't matter. So I go from 12 permutations to 6 combinations. Now you'll notice that I've been doing a lot of multiplying, and we have a function for that called the factorial. So a factorial, the symbol is the exclamation point. And if I put 4 factorial, that means the number itself times each integer less than it down to 1. And the 1 is really kind of optional because it doesn't do anything, but for completeness, it goes all the way down to 1. And so the example I used here was 5 factorial is 5 times 4 times 3 times 2 times 1. And we've got 20, 60, 120. Whoa, what did I do wrong? 20, 60, 120. I was wrong up here. So there's 120 options if you have 5 options and you order them all the way down. Now, one thing that's interesting is, and we will be using this as well, is that when we list them out, we can stop with any number factorial, and that'll cover the rest of them. So if I look at 18 factorial, right, that can be 18, 17, 16, 15, 14, 13, 12, ... Or I can stop at 15 and say 15 factorial, because that then means I've got the rest of the integers. You will see the value of doing this once we start having factorials on the top and the bottom of the equations in the next example. But this is taking us through factorials. The numbers get very large very quickly, and your calculator is going to have the button, but you will get quickly out of trouble or into trouble by overflow if you use any significantly big numbers with trying to do it with a factorial. So let's look at the formula for permutations. So for permutations, when the order matters, the way we write this is, the function is p, and you need to know n, the number of items that you have in total, and r, the number of items that you want to choose in your grouping. And then the formula is going to be n factorial over the number minus the number chosen factorial. And let's see if this makes sense. So if I look at the organizing A, B, C, and D into all of their different combinations, I had 4 total, and I chose 4. I used them all up. That's going to end up being 4 factorial over 4 minus 4 factorial, and 0 factorial is 1. It always needs to be there for things like this. And that means I don't reduce the number 4 factorial because I used them all up. Now for the second, when we did combinations of 2, we're doing 4 comma 2. So 4 total, choose 2. That's going to be 4 factorial divided by 4 minus 2 factorial, 4 minus 2 quantity factorial, or 4 factorial over 2 factorial, which is going to be 4 times 3 times 2 times 1 over 2 times 1. I can cancel these, and I get that 12 that we had back up here. The 12 different permutations of 4 items into a group of 2. So we did the permutations, 4 choose 2. Now let's do another example of, so if we have out of 7, we're going to choose 3 things. How many different ways can I do that? So my n is 7, and my r is going to be 3, and so I want permutations out of 7 choose 3, also written as p 7 comma 3. That's going to be 7 factorial over 7 minus 3 factorial, or 7 times 6 times 5, and here's where I'm going to do that, times 4 factorial, because I know what's coming on the bottom, divided by 4 factorial. And what this does, it just makes my algebra a lot simpler, because I can just cancel those rather than dealing with 4 and 3 and 2 and 1. And so I'm going to end up with 7 times 6 times 5, which is going to be 210. All right, any questions? You can't ask them anyway. If you do, however, put them in the chat, and I'd love to get to them. And then finally, we're going to look at combinations where the order doesn't matter. And so here we're going to look back at where we did our permutations and combinations for the 2-digit choices. So we ended up with 12 permutations and 6 combinations because we divided the number of permutations by 2, because a 2-digit unit can have 2 different ways, right? In order to choose them, you choose 1 of 2 of the first one, and then you're forced with the second one. So for 2, the total number of permutations of the 2 is 2, and those are all counted as the same. So when we go from permutations to combinations, we take the permutation answer and we then divide it by the different ways to arrange the chosen group, because all of those would be the same. So in this case, we're going to do combination out of 4, choose 2, right? Which is also shown combination 4 comma 2. And what we have is the total number factorial divided by n minus r factorial, which is the same as permutations, but then we also divide it by the number of different ways r can be sorted, because all of those are the same answer for combinations. So using this example, we're going to do 4 factorial over 4 minus 2, 2 factorial, times 2 factorial. So this ends up being 4 times 3 times 2 times 1 on the top, and then 2 times 1 and 2 times 1. So I'm going to get rid of both of those with the 4, and I'm going to end up with 6 combinations, which is the same thing we did. All right. Next we will look at a problem. And part of this is deciding what we want to do. So I have 20 raffle tickets, very small raffle. So 20 raffle tickets, and I'm going to choose 4 winners. Okay, each one wins $200. Okay, because the prizes are all the same, the question we want to know is, does the order matter? Does the order matter in how we choose the tickets? And the answer there is no, it doesn't, because every one of the winners, if you're the 4th winner, you get the same result as the first winner. So order doesn't matter. So we're going to use the combination formula. And our combination function is we have a total of 20, and we're going to choose 4 of them. So how am I going to do that? I'm going to do 20 factorial divided by 20 minus 4 factorial, also divided by, or multiplied in the numerator, in the denominator, times 4 factorial. All right, so now I'm going to do this, and I know that this 20 minus 4 is going to become 16. So on the top, I'm going to write, no, I'm not. On the top, I'm going to write 20 times 19 times 18 times 17 times 16 factorial, right? Because I've looked ahead and I know that this is going to be 16 factorial times, and here I'll list these out for canceling purposes, 2 times 1. So now I get my fancy canceling pen. I'm going to cancel those out. I've got a 3 and a 2 in the 18, so 6 out of 18 takes that to 3, and 4 can come to 20 as a 5. So everything on the denominator is canceled out, and I've got 5 times 19 times 3 times 17, and that equals 4,856 different ways to pick 4 winning tickets out of a 20-ticket raffle. And so setting up the equation is understanding the problem, and then after that, it's keeping track of your algebra. When to use your factorials, when to stop and leave it as a factorial is all something that will come with practice. And that is the end of the lesson. The next one will be learning about the binomial theorem and how to figure out if a thing can either be like head or tail, A or B, how to figure out things like, how do I know if I'll flip exactly 5 heads out of a 10 coin flip? So pay attention and like, subscribe, tell your friends, and take a look at the end. If you are looking for some personal math tutoring, give me a call at rockpiletutors.com. Thanks.